So here we go, results of part D, alpha part D. And we have open, closed, and reopened. So, hi ladies, good to see you. Excuse me. All right, now that that's over. So, what do you notice? What do you notice about the voltages here in this parallel circuit? They are constant. When the switch is closed, they're constant. You have the same voltage through the battery as you have across each of the bulbs. And that kind of makes sense when we think about our electron going around. It only goes through one of the bulbs. So remember, the current split, right? The current divided. So some of the electrons went up and some went down. They only encountered one bulb as they were going around. So it kind of makes sense that they'd have to give up all of their energy across that single thing that they encountered. Right? Yes? No? Dan, what do you think? Okay. So what is our general rule for this part 2 thing? For voltage in a parallel circuit? Okay. Now we probably kind of forget about the switch physics. You can leave that part off, but that would be fine. So you should make up a rule that has those types of ideas in it. Alec, what are you going to put down for your rule? What's always the same? Once you write it, then read. I think words that might be confused. Cookie, what are you putting down for yours? Okay, I would probably get the word parallel circuit in there. It might change light bulb to elements to make it more general. All right, anybody else want to check their rule? Here on the bottom of page 12. All right, then you'll want to flip to page 13. And on page 13, I would strongly suggest take a minute and put your 4 rules for your 2 for current and your 2 for voltage in the 2 different types of circuit. This becomes a great reference as we move forward. All right, so take a minute and write them down there. So on to beta, we use resistors as our elements. And so if you look at that first page, you'll notice that we have a circuit that looks fairly complex. And if we open up that same one in our simulation, one of the things, though, is we're really dealing just with this circuit here. We're dealing with a circuit that's made up of a switch, a single battery, and a resistor. Everything else that's here in the circuit is used to measure information about the circuit. Remember, the whole point of any circuit is to control the energy. So in this one, we're controlling the voltage and the current as we are with any circuit, so it'd be good to be able to measure those. Voltage being the difference in the energy the charges have on one side of an object compared to the other, we always use a voltmeter here to measure across an element. So like this voltmeter. Now, where can I find the symbol for a voltmeter in your packet? In the beginning of alpha, inside front cover, you have all of these symbols for your reference. Using those symbols to draw circuit diagrams are going to be a lot of your whys once we get up to doing problems in this section. So make sure you look through those symbols so you can reproduce them accurately. We'll get into that as we go through these things with you guys actually making the circuit diagrams. But for right now, they're created for you. So this voltmeter will measure voltage. Notice it's always connected in parallel to the object. What units would it measure voltage in? Volts. Yeah, volts. And then we have another voltmeter here to measure the voltage across the 15 ohm resistor. Remember you did the thing on resistors and voltages, such that all the resistors were measured in ohms. That's our base unit for resistance, and it has the symbol omega. So this tells you that this has a resistance of 15 ohms. And we're going to measure the voltage across it. And then, what do you think this meter that's down here on the side is? An amp meter, an and meter. We drop the P when we name it. So it's an and meter, and it would measure current. What units would it use? Amps. Amps is our base unit. Now, a lot of times, moving forward, we'll actually use milliamps, because milliamps ends up giving us numbers like 24, 50, 100.2 rather than 0.1 or 0.02 or things like that. So they're just more common sense numbers. But for right now, we're going to stick with amps. All of the meters here are designed and built so they do not change the circuit. So even though there's an and meter here in series, since the current has to flow through it, it doesn't change the circuit at all. It acts as if it's not there. The voltmeters are the same way. They do not change the circuit. So really, you are only dealing with this circuit, even though it looks like this, with your battery, with the voltmeter, and your resistor and the voltmeter and the and meter, and then the open switch here. All right? So we'll move on to symbols. And so we're going to, you're going to report in Cochran using volts and amps. Just put in the number. Like if you think the voltage across the 2-volt battery will be 3 volts, put in 3.00. You don't need to put in 3V or 3.00V. We can all try to stick to, hey, anything after, put in 2 decimal places. Then our numbers will be kind of consistent and we'll be able to look at them easily. But no, you don't need to put in units. They'll be in the question for you. Just put in values. But your prediction is when the switch is closed, what will be the voltage across the 2-volt battery? What will be the voltage across the 15 ohm resistor? And what will be the current through that and meter? That's in amps. That's what you're predicting. All right? And then you have a couple of questions about it. I'll turn on Cochran right now, and you can go through the prediction, unless there are questions. All right, sit down and look at the results. All right, so here are the here are the kind of the summation of the predictions here in A. Looks like the majority of people think the voltage across the 2-volt battery will be 2 volts. Kind of makes sense a little bit. Although we have a couple people that say we have one person who says it'll be 1 volt, one person who says the voltage across the 2-volt battery will be 7 volts, and another one says 5 volts across that 2-volt battery. All right. So good, some variety there. How many volts across the 15 ohm resistor? Majority, well, it's kind of hard to pick out a majority, but I'd say the majority think there'll be 15 volts across the 15 ohm resistor. Oh, I wonder if that's why. Because a lot of people think, I see the number 15 in the name of it, so it'll be 15. I someone who says 0.5 volts, someone who says 30 volts, someone who says 2 volts, and then 13, 7.5, another 2, another 30. I'm interested, would someone share how they got what they got? Unless it's I saw the number 15, so I picked the number 15. That's for choice. Why do you think the voltage would be the same across all elements? Okay. So that brings up a good question then. What type of circuit for the voltmeter is that? What type of circuit is that? Is that a parallel or a series circuit? It's actually neither. Because to have something in series, you have to have two or more things in the same line. And to have things in parallel, you have to have two or more things in parallel with each other. How many elements, besides the battery, do we have in the circuit? How many resistors? 1. So can it be in parallel or series with itself? No. Okay, so but you were thinking about alpha, right? I kind of cut you off there. Sorry about that. And you were saying because there were 2 volts in the battery, there are 2 volts across here. Okay. I can see the logic in that. How did someone get 13? If they share. Not, that's fine. Okay. So a little subtraction there. What about our 7.5? Is that 15 divided by 2? Okay. Alec, sorry, you have your hand up. Okay. So you had, what was your answer then? What did you have what was your prediction? Okay. Where'd you get the 0.5 for the volts then? Okay. All right. Then in our ammeter, we seem to have a lot of variety. From, let's see, our highest looks to be 60 amps, and our lowest 1 amp, maybe. Yeah. Okay. Anybody want to share how they came across the amp? You guessed. Okay. What did you guess? Why did you guess 5? Okay. No, this is good. We're looking for what ideas you use. So, anyone else want to share how they got their value? No? Hey, is it blank? Then is it wrong? No, so don't tell me it's wrong when it's not. Okay. Well, that was used somewhat to get some of the voltage across the resistor, right? Because we did 15 and -2, so why not take 15 and add 2? Yeah, okay. I see what you did. All right. Well, let's go to the actual results and see what the universe does as the correct answer, and then we'll see the skills that we're going to use after that. So, so here we go. The correct results. Oh, look at that. How many volts across the 2-volt battery even before I hit the switch? 2, because would that change is that going to change when I hit the switch? No, remember we saw that in all of them? But I hit the switch and now I get current. negative 2 volts and 0.13 amps. How many places do the electrons that are moving around the circuit have to lose energy? Anywhere else besides the resistor? No, because the switch is just wires. We're going to assume that they don't use any energy. So only the resistor. So if it's got 2 volts of energy, and the only place it can lose it is the resistor, how much is it going to lose across the resistor? Yeah, and that's why it's negative. Just to keep the idea, and that's something new, that if the battery is giving the electrons energy, the resistor is taking away that energy. And that's why it's negative. Yeah. What would it be? Negative 15. If it was a 200 volt battery, what would it be? Negative 200. If it was a 1 volt battery. Now, most of the time, we're just going to worry about the magnitude. The idea that I wanted to get across by arranging it so it was negative, is that it's using energy, and the battery is producing energy through the chemical reaction. So, like in the previous circuit, how could we tell that the light bulbs were using energy? They were producing light. Last week, you did 3 simulations in a little interactive lab. The first one had a battery and a resistor. How could you tell in that simulation that the resistor was using energy? The amount of heat, it got hot. And that's how resistors use energy. They use it and make it into heat. All right? So this 15 ohm resistor is using 2 volts per coulomb, 2 joules per coulomb, which is actually what a volt is, of energy as these electrons move through. The only place for it to lose it, so it has to lose it all there. All right? Bigger question, how do we get that 0.13? Well, let's see, we've got a couple of numbers here. We have the number 2, we have the number 15, and we have the number 0.013. Is there any way to relate those 3 numbers together? Like, let's see, 2 times 15. Is that 0.13? No. 2 divided by 15? 2 over 15 equals 0.13. Is that true? Anyone want to double check? Verify? Hi. No problem at all. Is that true? Yes, I get a thumbs up. All right. What was the 2 measuring? Voltage. So, let's see, our symbol for voltage would be V. What was the 15 measuring? It was measured in ohms. What was that measuring? What was that? The resistance, R. And what's the 0.13 measuring? It was measured in amps. Current. Oh, I hate fractions. V equals IR. Did we see that anywhere before? Last week in that three simulation lab. That was the 3rd simulation, wasn't it? Anyone remember the name of it? Out of curiosity? Named after a gentleman? Ohm's Law. Ohm's Law. Named after Dr. Ohm. And hence, what's resistance measured in? Ohms. Why do you think? Because that dude. So that's how, this is the relationship you guys explored and discovered last week and played with, that the voltage across something equals the current through it multiplied by the resistance. So how much energy something loses going through an object, like the 15 ohm resistor, is based on the rate the current moves through it, the rate the charges move through it, the current, and the resistance to that motion. So you played with it with the resistivity and the little dots and everything like that last week. So there's your refresher on Ohm's law. Any questions about that relationship? This is a big one, so make sure that you understand, you see it. Really, really critical. All right. So, in the last part of this page, we're going to do a couple of skills that eventually will become part of your whys, part of your showing you conceptually understand the problem. And they're also going to be the way that then helps you be able to set up the equation to solve any circuit. And they're called drawing the current and plotting the voltage. The current we're going to represent by arrows, since it's a flow of charge, the way the charges move. The voltage, because it's energy, we're going to represent it by heights, like we would think about it like a roller coaster, and you'd have gravitational potential energy. This will be electrical energy, but we're going to show it very similarly. So, to draw the current, really all you need is any drawing of the circuit. It could be a pictorial drawing like this one, or it could be a schematic drawing like we had before. What if I left it off of that drawing? The meters, because they're just giving us information. They don't influence the circuit. And then here I've drawn that same circuit, but now drawn it three-dimensionally. Because I'm going to have to draw heights up off of it, it needs to be a three-dimensional drawing. Because two dimensions won't do it anymore. So we're going to go through these skills, and in this part, they'll be part of our results. But then when we get to part gamma, they become part of your predictions and your why. All right? They're also in the video. They're gone through in the video that you're going to watch tonight. So let me open up. So here we have that drawing. And how many currents in this circuit? One. There's one current. That's why we had one ambient. Now, current flows in, the rule for it is it moves in the direction a positive charge would move. We know the current is made up of electrons, but they didn't know that when they first established the convention. So it's the direction a positive charge would move. Do positive charges like to be near each other? No. And that's why this side of the battery is labeled as positive. So our current is always going to flow out of the positive side and into the negative side. So you want to represent that on your drawing there on page 15 by arrows. And since there's only one current in this, we would just label that as current number 1. Or if you're really feeling an economics of writing, you just label it as I rather than I1. You You want those arrows right on the wires because you want to make sure you realize that the current is flowing through those wires. Any questions on how to draw the current at this point? Excellent. So the next skill, the next conceptualization is, oops, and labels have already appeared. I have to go back and fix that. Is to plot the voltage. To do that, I have a 3D representation. I have my resistor and I have my battery here. I start off by putting in my currents, and the labels that are in there would come in last. The slideshow must have gotten a little bit, the order must have gotten messed up a little bit. But I'm going to represent how much voltage, how much energy each charge has by the height. And I'm going to start here at the positive plate of my battery and give that a height of 2 volts. And so I'm going to draw a line that's 2 units tall. Whatever in your mind represents 2, draw it that tall. Now remember, voltage always measures difference. So if this side of the battery is 2, that means the negative side of the battery must be, you want a difference of 2. 0, 0. Right, you could pick 4 or you could pick 0, but if you're moving this direction, you're moving with current, a battery you're always going to go up, and a resistor you're always going to go down. That's why we represented it mathematically as negative. So that means positive side of my battery is 2, the negative side is 0. What if the negative side was negative 50? What would the positive side be then? The negative side was negative 50. The positive side would be negative 48. If the negative side was 10, the positive side would be 12. Try another one. The negative side was 1. The positive side would be 3. The negative side was, give me a number, Kim. 8. The positive side would be 10. Olivia, give me a number. The positive side is 7. What's the negative side? 5. Yeah, I did change it around. Aiden, you got that, you think? Okay. So, if here's at 2 volts, and from here to the next corner, there's nothing to use up or give it energy, that means the front corner is also at 2 volts. So I draw another vertical line that's 2 volts tall from that front corner. Is there anything from the front left corner to the front right corner to use up any energy? Is there anything from the front left corner following along that wire to the next corner to use up energy? No. So that means that this front right corner is at 2 volts also. What about from the front right corner to the back right corner? Nope, so that one is at 2 volts also. And all the way up to the front edge, the right-hand edge of my resistor. So all of these blue lines are at a height of 2. Because that's how much voltage the electrons would have at that point. What's the voltage again at the negative side of my battery? 0. So is there anything between that negative side and the back left corner to take away or give energy? No, there's just a wire. From here to here. Just a wire. What about from that back corner to till I hit the resistor? Nothing. So If I want to represent zero, Sam, how tall of a line would I draw? Nothing. So I've drawn my lines, right? I've got all my heights represented to show the voltage changes, to plot for voltage. Now what I do is I connect all those lines. So I've connected the tops of those lines to create a representation of the voltage as it changes around the circuit. And what that would allow me to do is, if I think about it, I think of myself as an electron, I start up here, I travel around on this little red line, all happy because I have 2 electron volts of energy. I get to the resistor, I got to give up those 2 electron volts of energy. And then I keep traveling around, and then I go across the battery, and whee, I get it back. Think of it kind of like a roller coaster, analogous to a roller coaster, and how your gravitational potential energy changes. Any questions on plotting the voltage or drawing the current? Both of these will be skills that will help you be able to analyze the circuits as we get more complicated. So, series circuit, looking at voltage, 3-volt battery, 10 ohm resistor, 22 ohm resistor. What are going to be the voltage across the 3 elements when the switch is closed? In the interest of time, I'm going to have us finish that. And let's look at what people put as results. So looks like everybody predicted, oh no, sorry, I was wrong. Most people predicted that the voltage across the 3-volt battery would be 3 volts. See if I can get this a little bigger so you guys. So most people predicted 3 volts. We had one student who thinks the voltage will be 2 volts. All right. But I think given the majority, we'll just move on to the voltage across the 10 ohm resistor. We have answers from 3 to 0.3 to -3. Oh no, negative a lot, 0.3. Looks like some functionality of 1.5 seems to be the norm. 1.5 or -1.5. Anyone want to explain their thinking on who maybe picked 1.5? What was you thinking? Is that the rule you have on 13? Okay, okay. I was just checking that. Okay, so, and since it says evenly in your rule, it's split up evenly. Okay, I can see that. All right, was that most people's thinking on the 1.5? All right. What about the 0.3s? Okay, let's move on to the 22 ohm resistor then. So that means the 22 ohm resistor is about twice as hard to get through as the 10 ohm, right? That's what the resistance is indicating. So it's twice as hard to get through that 22 ohm resistor, or a little more. Okay, and we have very similar answers. Okay, I can understand that. I'm wondering if the people who said 3 for each thing were thinking about that this was a parallel circuit. Because in parallel, what is the voltage? Stays the same. So make sure on 13 that you didn't mistakenly put down the rule in the wrong place. So check that your rule on 13 for a series circuit, the voltage divides or splits or something like that. Just double check that, because you don't want to have copied it in the wrong place, you know. So good. All right, we will pick up at the top of 17 next time and see the results for part B of beta when we get back from vacation.